All right, let's dive right into this explainer and completely transform how you look at the fundamental rules of mathematics. We're going to explore the hidden architecture of numbers today, going from unbreakable absolute rules to some seriously mind-bending plot twists. By breaking these concepts down into simple, logical steps, our goal is to give you a crystal clear understanding of the entire topic in a way that's easy, effective, and honestly, a lot of fun. So I want you to imagine numbers for a second, but not just as abstract symbols on a page. Think of them more like physical structures. Like giant, complex buildings made up of foundational ingredients. If you were to take a mathematical hammer and smash a massive number apart, what would actually be left in the rubble? Well, today we're going to find out exactly what those base ingredients are and how they literally govern the entire mathematical universe. Here's our roadmap for today. First step, math's ultimate building blocks. Then, the fundamental theorem. Number 3 is cracking HCF and LCM. 4 is the irrational plot twist. And finally, number 5, proof by contradiction. Let's get into it. Section 1, Math's Ultimate Building Blocks, Discovering the Atoms of Arithmetic. We're going to start things off by treating prime numbers like they are the ultimate Lego pieces of the mathematical universe. You know prime numbers, right? 2, 3, 5, 7, 11. They're the numbers that can only be divided cleanly by 1 and themselves. They totally refuse to be broken down any further. They are essentially the indestructible atoms of arithmetic. Okay, so the absolutely crucial takeaway here is what this definition tells us, the fundamental theorem of arithmetic. It states that literally every single composite number, meaning any number that isn't a prime itself, can be built just by multiplying prime numbers together. And here is the magic word, unique. No matter how astronomically large a number gets, there is one, and only one, unique recipe of prime numbers that can build it. To really put this into perspective, let's look at a pretty massive number, 32,760. If we use a factor tree to break it down, dividing it by its smallest primes over and over again until we reach the bottom, we're left with 2 to the power of 3 times 3 squared times 5 times 7 times 13. This is literally its mathematical DNA. Nobody in the universe will ever find a different set of prime numbers that multiply together to make 32,760. It's locked in. Moving right along to Section 2, the fundamental theorem, the history and application of prime factorization. Understanding a bit of the history here really helps us appreciate the mechanics, and then we're going to use this exact theorem to solve some incredibly cool practical puzzles. Before we actually use it, we absolutely have to give a shout out to Carl Friedrich Gauss. Now, while the ancient Greek mathematician Euclid kind of danced around this idea way back when, it was Gauss who laid down the first completely correct, rigorously documented proof in his book Disquisitiones Arithmeticae. The guy is often called the Prince of Mathematicians, and for good reason. This cemented his legacy right up there with absolute legends like Newton and Archimedes. Thanks to Gauss, we know we can trust this rule completely. All right, let's test drive this theorem with a quick logic puzzle. Imagine the number 4 raised to literally any natural power you can think of. We'll just call it n. 4 squared, 4 to the 10th, 4 to the millionth power. The question is, will any of these results ever end in a 0? Now, here's what's really fascinating. We can use the absolute uniqueness of the theorem to definitively prove this is impossible, without having to calculate 4 to the power of infinity just to check. Basic math tells us that to end in a 0, a number has to be divisible by 10, right? Which means its prime DNA absolutely must include a 2 and a 5. But 4 is just 2 times 2, so 4 to the power of n is just an endless repeating string of 2's multiplying together. There's 0 chance of a 5 being in that recipe. Therefore, because of the fundamental theorem, we know with 100% certainty that it is mathematically impossible for it to ever end in a 0. No way! Section 3. Cracking HCF and LCM. Using primes to solve greatest common factors and lowest common multiples. Let's scale up that Lego metaphor we talked about earlier. What happens when we have 2 different numbers and we want to compare their DNA side by side? Well, we can use the prime factorization method to effortlessly find their highest common factor, the HCF, and their lowest common multiple, the LCM. Let's untangle this side by side using the numbers 6 and 20. 6 is just 2 times 3, 20 is 2 squared times 5. For the highest common factor, we just scan for the primes they actually share, which in this case is only 2, and we take the smallest power. That gives us 2. Simple enough. For the lowest common multiple, we take every single prime involved across both numbers, so 2, 3, and 5, and we grab the greatest power of each. That's 2 squared times 3 times 5, which perfectly equals 60. And because these prime numbers interlock so perfectly, we actually get a literal mathematical cheat code out of it. Definitely keep this shortcut in your back pocket. For any two numbers, if you multiply their highest common factor by their lowest common multiple, it gives you the exact same result as if you just multiply the original two numbers together. It is such a beautiful, symmetrical rule that really highlights how elegantly the world of prime numbers is designed. Section 4. The irrational plot twist, when the rules of fractions break down. But of course, just when we think we've got the universe neatly packed into these easily understood rational fractions, we hit our narrative plot twist. Enter irrational numbers. These are the absolute rebels of the math world. They're numbers that cannot be written as a simple fraction, whose decimals just go on forever and ever without repeating. Before we can catch an irrational number red-handed, we have to play detective and equip ourselves with a vital mathematical tool from the text. Theorem 1.2. It states this: if a prime number divides a squared number, it absolutely must divide its root. For instance, if the prime number 3 divides 36, which is just 6 squared, right? Then 3 must also divide 6. It's a remarkably simple, undeniable fact, but it's going to be our secret weapon. Section 5, proof by contradiction, cornering the square root of 2. All right, it is time for the climax of our explainer. For thousands of years, the square root of 2 has haunted mathematicians. Today, we're going to definitively prove that it's irrational, and we're going to do it using this brilliant psychological trick for numbers called proof by contradiction. Basically, we're going to assume the square root of 2 is normal and watch as it accidentally destroys its own alibi. Let's walk through this step by step. Step 1, we assume the square root of 2 is just a regular, rational fraction a over b, and we assume this fraction is fully simplified, meaning a and b share absolutely no common factors. Step 2, we square both sides to get rid of the root, which leaves us with 2 times b squared equals a squared. Step 3, okay, because a squared is equal to 2 times something, a squared has to be an even number. And based on that secret weapon theorem we literally just learned, if a squared is even, a itself must be even. So a is just 2 times some other number, let's call it c. Step 4, we substitute that back into our equation, and the math reveals that b squared is also even, which means b is also even. And step 5, boom, the trap snaps shut. If both a and b are even numbers, they are both divisible by 2. But wait a second, our very first assumption was that they shared no common factors. We just forced the math to completely contradict itself. The only logical conclusion here is that our first assumption was wrong. The square root of 2 cannot be written as a fraction. It is undeniably 100% irrational. And you know what's really wild? Once an irrational number enters the chat, it acts like a mathematical contagion. It completely infects the whole equation. If you add, subtract, multiply, or divide a normal rational number with an irrational number, like say 5 minus the square root of 3 or 3 times the square root of 2, the result is always going to be irrational. That endless, non-repeating chaos of the irrational number just takes over everything. Well, that brings us to the end of our journey through real numbers. We've gone all the way from the comfortable, perfectly organized Lego bricks of prime factorization to actually proving the existence of chaotic numbers just by forcing math into a logical paradox. So I want to leave you with this final thought. We've just seen how logic can be used to prove the impossible and catch numbers that completely break the rules. So what other hidden truths, anomalies, and paradoxes do you think are out there, just waiting to be uncovered in the infinite world of real numbers? Keep questioning the foundation, guys, because that is exactly where the greatest discoveries always hide.